This is a view of an early development of our connectivity in the NeuroNavigator with swLORETA. What you see here is the MRI from the surface, and the spheres are the center voxels, really surrounding the center voxels of 88 Brodmann areas. Even though these are single voxels, because it's low resolution electromagnetic tomography, the spheres basically look at the extent and a centimeter or so of sources, and we can change the size of spheres. The colors it can be changed, but also the lines between the spheres or the Brodmann areas will change depending upon the magnitude of the coherence or the phase differences, because this is effective connectivity. As you can see, we can rotate the brain. We can also look at the current density at the surface simultaneously while viewing the connectivity. We can do this eventually in real time. For now, this is edited data that has been imported into the NeuroNavigator with swLORETA, and we can move these things around a bit and allow it to take different forms and also have scalp and skull removed or slicing through the brain with all the other various tools that we have. So we can also use the slicing tools that go to axial, coronal, sagittal, and horizontal slices. So all the other tools that are in NeuroNavigator are active as well, but there's the scalp and the shape of the head. We can alter the settings so you can look at different z-scores or current densities. We're going to adjust the z-scores here a little bit so you can look at a wider range of scores. Both raw scores and z-scores can be evaluated using this tool of functional connectivity. And then we also will have effective connectivity, which is the magnitude of information flow between these different nodes. We can also go with swLORETA from the surface of the cortex down to the bottom of the cortex in 10 steps. And so this is an introduction to the capability of these new capabilities we're building with functional and effective connectivity. With the various tools inside of NeuroNavigator, we can make the skull completely transparent and then just look at the nodes in the network. You can go back and forth, rotate just the nodes in the networks. You can select particular networks based upon the symptom checklist and the networks that you select. For example, the anxiety network, the memory network, the mood network, etc. And then you will limit the number that you will see, because this is the full 88, and it is not as useful as identifying subsets based upon the networks that are linked to the patient's symptoms. Now, the functional connectivity and effective connectivity project is well underway, and we expect to be complete with this in a month or two or so. And then we'll begin to add diffusion tensor imaging to the NeuroNavigator as well, with controls that, again, will be linked to the networks and symptoms, but that will provide the undergird, sort of the infrastructure of the EEG, because we'll be able to then see the current density and electrical potential from the scalp surface in a transparent skull that we can cut through, and also then see the brain inside the skull, and then the connections between the 88 Brodmann areas. Then we can also link that to a particular diffusion tensor imaging based upon the DTI, diffusion tensor imaging atlases. Right now we're working with one particular one, but the Catani and Deschatten atlas is an example of a very good diffusion tensor imaging atlas. But the important thing is that we eventually will be able to add diffusion tensor imaging to give a different perspective, a structural relationship of the white matter with endpoints being the sources of the current density in the cortex, both in raw scores and with z-scores. This is just another view of the diffusion tensor imaging from the horizontal axis. And again, we'll have views of the diffusion tensor imaging inside of NeuroNavigator that will include the coronal, horizontal, and axial slices, as well as the volume of the of the cortex. This is another volume view of the diffusion tensor imaging. We'll be working on this so it'll be more clear than this, because we can control the depth of view, so your view is not blocked in the three-dimensional volume view. In any case, this is a work in progress. That will be our endpoint. This is probably 5 or 6 months down the road, because the first thing we're going to get working are the node functional connectivity and information flow. The effective connectivity will allow you to see both the direction and magnitude of information flow using the phase slope index from the center voxels of the 88 Brodmann areas, the origin of the information will be green on the line, and then it's the direction it's going to and terminates at will be colored red. So it'll give you some idea of the direction, and then the colors in between the endpoints of the effective connectivity will be z-scores that are signaled by the color of the line and or the thickness of the line. Right now it's just going to be the color of the line. This is the cutting tools showing the volume and the connectivity. Now we got different themes. I'm going to turn that, or Ernesto's going to change it so it's a dark mode, which is quite interesting. It allows you to see the view, both the currents, the contour of the brain, scalp, and then the connectivity inside the brain with these different nodes and lines between the nodes, showing the connectivity. And of course, you can make the brain transparent so that you have only the connections, and then you can also add skull and scalp, as I mentioned, with the Laplacian surface or the electrical potential, and you can also go into the top and bottom of the cortex itself, although the connectivity only can be from the center of the Brodmann areas. It's not going to be changing for the upper layers of the cortex or lower layers of the cortex, just the center. This is low resolution electromagnetic tomography, and the center voxel is representative of the Brodmann area. If you take the average of the voxels, or the current density, or the z-scores, then there is uncertainty at the boundary of one Brodmann area to the next Brodmann area that's adjacent to it. Whereas if you evaluate the currents and the connectivity from a center voxel, it's a single voxel, that is correlated with its neighbors, but it diminishes as a function of distance as you get to the boundary of the adjacent Brodmann area. So this is an example. We're just playing around with this color of making the cortex transparent and the scalp transparent, so you can see the networks. This is an example where we have added the skull. Of course, you can go all the way up with the cutting tool to the top, and then add current to the scalp, or at least electrical potential from the EEG on the scalp. And as I mentioned, also there's a Laplacian option So you can look at the current density computed by the two-dimensional Laplacian transform. So this is just another view as we begin to develop these tools that will be available in a few months. So I'm going to sign off, and I hope you enjoyed this little initial foray into the future of connectivity with swLORETA and the NeuroNavigator.